So my name is Nicholas Christian. I work for a company called Datacratic here in Montreal, where we specialize in machine learning, and we work on a product called the Machine Learning Database, MLDB, which has support for all sorts of neat algorithms, some of which I'm going to talk to you a little bit about today. It's not a corporate presentation or anything, but I'm here to talk to you about dimensionality reduction as an alternative to graph visualization. And if that's all kind of gobbledygook to you, hopefully I will demystify these words by the time the presentation is over. So this is what I mean when I say a graph. I don't mean a graph like a line chart. This is sort of what a computer scientist would refer to as a graph. You've got two little circles here, hello and world. We call these nodes. You can think of them as things, elements, whatever you want. And the line between the two of them, connecting them, is sometimes called an edge or an arc. You can think of it as a connection. So here, hello is connected to world. Enough said. Graphs are pretty easy to visualize. If you have a bunch of nodes, you can lay out your nodes in a line. You can actually draw the connections between them. There's a whole bunch of tools that exist to do a whole bunch of different types of graph visualizations or graph layouts. So here you've got them all in a line. Here you've got them all in a circle. You connect them lines. You can connect them with curved lines. You can connect them with straight lines. And here the kind of decisions you're making are kind of like, well, what order do I put the nodes in, right? There's tons of tools that exist for doing this, which is really neat. One of the most popular and easy to use ways of laying out a graph is called a force-directed layout. So a force-directed layout, this is a typical output. You may have not known what it was called, but that's what it's called. What it is basically you think of the nodes as like being little magnets that push against each other. You know, when you put like magnets end to end. And the links between the nodes, the edges, kind of pull them together. So when you kind of balance out the forces of the nodes that push each other away and the edges that pull them together, you get this kind of layout. And so basically here, you kind of have all the nodes that kind of push each other as far away as they can get while still being caught by their edges. This is a very popular kind of visualization. It's very neat. I think there's sort of two reasons why people like them. This is my hypothesis. One, it's got kind of a knee bone is connected to thigh bone kind of feeling, like, hey, I can see the line. This is connected to that. And the second thing is that a force-directed layout will put basically nodes that have a lot in common will all be kind of clustered together. By and large, nodes that don't have a lot in common will tend to be far away from each other. And this is kind of like a map-like property, right? What's the basic property of a map? Well, things that are close together on a map are close together in real life. Things that are far apart from each other on a map are far apart from each other in real life. So this is kind of a neat property of a force-directed layout. This is a pretty simple graph layout of my social network according to Facebook a few years ago. Each little dot with labels that are unreadable to you from that distance is basically one of my friends. And so, by the property of things that are close together are similar, you can see that, there's at least, call it 4 little subgroups within my social network. That sort of hyperactive blob of people all on top of each other is a student organization I used to be part of called Engineers Without Borders when I lived in Toronto. Over there is my friends from Toronto. Here are my friends from high school. I didn't go to high school in Toronto. And then at the bottom here is my little embryonic Montreal social network. So I have a lot more friends in Montreal now. I've been here for about 8 years. So this is pretty typical, right? And it's pretty nice. The data set is pretty simple. I have friends. Some of them are friends with each other. Anytime 2 friends of mine are friends with each other, there's a line. And that's all it is. And so this is pretty trivial to generate. Like this is just some of the default settings from a tool called Gephi, G-E-P-H-I. In case any of you are interested, it's really neat. So this is essentially arguably the same topic, slightly different data set. What I did here, this is the output of some visualization that I did for Hack Montreal, a hackathon about 8 years ago. What I did here is I scripted my inbox. So and I wanted to visualize my social network based on my inbox. And so I was like, oh, hey, Gephi's really easy to use. It makes nice layouts. I'm gonna pop this in and do a graph visualization. Except I had a bit of a problem. Is that in my inbox, I don't know who's friends with who, right? All I have are email threads. So what I did was I decided to, I'm not sure if it's super visible, but the red dots here are individual email addresses. So they basically represent people. And the little white dots represent actual email threads. And so people are connected to emails. People aren't connected to each other. And emails are connected to people. Emails aren't connected to each other. And so what happens is that if 2 people are often in a CC list of the same email, they essentially get pulled together. And you see roughly the same structure, right? You see this sort of big hyperactive blob in the middle. That's Engineers Without Borders. All this stuff over here happens to be laid out in the same way. That's my social network from Vancouver. And then down at the bottom is my family, none of whom is on Facebook. So this is kind of the same thing, and it's neat. You can get lots of kind of neat output. And people use these techniques all the time, right? So here's a neat visualization I found online. It's basically a map of science. So here, every dot is a journal full of peer-reviewed articles, and this is basically meant to be a map of how these journals all connect to each other. So there's there's nodes and edges, and it's a nice visualization. You've got kind of the hard sciences over on the far side there, physiology and stuff in the middle, a lot of the social sciences in the middle. Medicine and biology and stuff at the bottom. And so this looks really great, and it's pretty appealing, and it makes for a nice kind of infographic style thing. Except you kind of got to wonder why are there lines between certain journals? I mean, journals aren't friends with each other, right? I mean, journals are basically collections of articles, and articles cite each other. So this is kind of like a citation graph, but there's thousands and thousands of articles. There are many more articles than journals. Now, I don't mean to harp on this visualization, it's very nice, but I want to kind of unpack it a little bit. What's happened here is that basically someone decided that if a certain number of articles within a journal cite other articles within another journal, that merited a connection. And so each individual line here is kind of arbitrary, right? You could have had two journals that just had one less citation, but they didn't get a line. And so that line didn't get the tug. And so the structure might have been slightly different. So in this particular case, my evaluation is that someone decided that graph visualization, a graph layout algorithm would be an easy way to make this, and they said they kind of shoehorned the data set to fit into the input of a graph visualization tool. And there's nothing criminal about that, but it's kind of an interesting thing to note. And that's become quite popular, right? You go to look at visualizations like this, which are basically layouts of the tags on Stack Overflow. So each circle here is a question tag on Stack Overflow, and basically the same logic was used. If two tags share enough questions, they get a line, and then you pop that into essentially the D3 force-directed layout, and you get this visualization. But it seems a little arbitrary. I mean, here you got C# is connected to Python essentially by a thing called list. List isn't connected to Java. So there aren't enough questions that have both the list tag and the Java tag. It seems a little bit arbitrary. It's not like lists are particularly more C#-ish than Java-ish. So that's kind of something a little bit interesting to think about. This is another example of kind of the same style of thing. This is essentially a map of Reddit. So Reddit is a large discussion board full of little sub-discussion boards. Each little circle here is a sub-discussion board. And the data being visualized here, this is from a from a paper, is basically any time that two subreddits had many users that posted many times to both, they merited a link, and then this is what came out of a graph layout algorithm. And so the person who wrote this article went and sort of called out certain clusters. So you've got the electronic music cluster at the top, pornography is a big thing on Reddit, sports over there at the edge. And it's kind of neat to look at. When you zoom in to the sports cluster, you see this. So you see NFL, NBA, baseball, and then a whole bunch of links to different teams. And then in the back, you see other links that are from stuff up there that are to stuff down here. So this is kind of using a force-directed layout to make a map, to bring things that are similar close to each other. And then they kind of draw the lines on. But the lines are a little bit arbitrary, right? Because in order for there to be a line between two things, you had to have some number of users in common. So kind of begs the question to me, why even draw the lines? Why bother with the lines, right? And the lines are arbitrary, and the fact that the two things are related to each other is already visually encoded by the fact that they're close to each other on the graph. The lines aren't really adding much except noise. So that's just kind of something to think about. So the lines are arbitrary. You don't really need to draw them. Do you even need to use a graph layout algorithm to get this kind of output? To get output where you have essentially a bunch of dots that represent, say, subreddits, and similar ones are close to each other. And the answer is no, you don't have to use a graph visualization algorithm. There's nothing wrong with it, but there are some other approaches which have some nice properties, one of which is dimensionality reduction. So I'm going to kind of introduce dimensionality reduction via an analogy that I think everybody can kind of wrap their hands around. Basically, cartography. Cartography is pretty old. People have been making world maps for about 2,000 years. The basic intuition is that the Earth is a sphere, right? This shocked some people in the Middle Ages. The Earth is a sphere, so technically the coordinates of a whole bunch of points on the Earth are in 3D, right? But when we make a world map, maps are in 2D. And so we kind of have to take a 3D set of data and make a 2D representation of it. And we don't do that by kind of saying, well, any 2 points which are closer than a certain distance apart, get a line, get a connection, and then use a graph layout algorithm to do that, right? No, we use kind of various types of equations and geometry to make what everybody recognizes as a world map. So this is a sort of equirectangular map projection. Everyone kind of knows what that is. But there are also sort of other exotic ways of representing a world map which are equally valid. So what you see here is an azimuthal projection, which is essentially what's used in the United Nations logo. Every kind of 2D representation of the Earth has some distortion to it, right? Everybody knows that the Mercator projection or this kind of equirectangular projection, you know, Greenland is nowhere near the size of Africa, but it looks kind of close on this map. In this particular case, the distortion here is that Antarctica got turned into a ring. In the United Nations logo, they get around this by just putting a laurel leaf and just not having Antarctica. So there's different kinds of trade-off, different ways of projecting 3 dimensions into 2 dimensions. And you get certain problems with that, right? Certain things which really should be close to each other on a globe aren't close to each other on a 2D map. So it turns out that there are a bunch of algorithms that exist that allow you to take high-dimensional data, where the number of dimensions is much more than 3, and turn it into low-dimensional data, like 2-dimensional data, like a graphic. This is taken from the scikit-learn documentation. Scikit-learn is a really neat collection of machine learning algorithms for the Python programming language. And what we're looking at here is, this is the underlying data set here. It's sort of like an it's sort of like a plane that's been curved into an S shape. So it's a set of three-dimensional points, right? Coordinates in a 3-dimensional space. And then each of the little boxes on the side there are basically the output of a particular algorithm run on this input. So we've basically asked some machine learning algorithm to take this 3D input and reduce the dimensionality down to 2. So you can see that different algorithms take different approaches, right? This LLE thing in the corner, I don't really know what it did, but it kind of made decided that the S shape was cool. And the S down here really focused on the fact that the shape was an S. Whereas a lot of the others basically kind of figured out that actually, well, it's a plane that's been curled into an S, right? So it kind of focuses on reducing the dimensionality by kind of un-S-ing the sheet. And the bottom one, the far right there, called t-SNE, basically kind of tries to play the middle ground, right? You got a bit of an S shape, and yet you got a bit of a linearity to it. So this is the algorithm that I use fairly often. t-SNE is how I pronounce it. I don't really know if it's pronounced any other way. It stands for t-stochastic neighbor embedding, but you don't need to remember that. So this is all very abstract. What does it mean? Well, I took essentially the same data set as the Stack Overflow tags visualization I showed earlier, and I basically ran it through t-SNE, and this is the output. Now I kind of prettied it up with colors, but essentially what you're looking at here is I took 50,000 questions from Stack Overflow, and I said that each of these 50,000 questions is like a dimension. So when you're looking at a 3D space, you know, where essentially each point is, say, a city in the world, here I have a 50,000 dimensional point for each tag, right? And so each tag either belongs to a question or it doesn't. So it's a very high dimensional binary space. And I asked the algorithm, please put this down to 2 dimensions for me so I can look at it. And this is what came out. And so some commentary on this. First of all, you see that each dot here is a tag on Stack Overflow. You see that they kind of cluster into little groups. And if you kind of drill in and kind of, the original version of this is you can sort of mouse over and look at what each dot is. You can kind of go and figure out that there's little clusters, right? And each little cluster kind of corresponds to some subset of some dimensionality of the data. So if I ask people to sit down and sort of categorize or write down a taxonomy of Stack Overflow questions, there's a whole bunch of different equally valid ways of doing it, right? You could say Stack Overflow questions belong to a certain language and sort of bin them by language. You could say they belong to a certain aspect of programming, security, performance, logging. You could say they relate to a certain sort of application domain, like dates and times and math, or certain computer science concepts. So what the dimensionality reduction algorithm here did is it essentially grouped all the different tags according to some semblance of similarity to other tags. And so in some cases, like over here, the blue thing, it says date time. So all of those tags over there are related to date time. And the programmers, dates and times, sorry. The programmers in the room here know that basically dealing with dates and times is sort of its own particular circle of hell, no matter what programming language you're using, because humans are irrational about how they think about time. You got some clusters at the top, Git, Vim, version control, Eclipse. These are all sort of connected topics. You got a whole cluster of questions around Git, which is, they're all similar to each other, and they're near kind of the cluster around version control. They're near the cluster around Vim. So you've already got some sense of what the dimensionality reduction algorithm did, right? It essentially grabbed a bunch of stuff around dates, put them together, a bunch of stuff around tools, put them together. Down at the bottom, you've got iPhone, iOS, Xcode, Objective-C, iPad. It's kind of pulling out the relationships between operating systems, languages, domain of application. So it's kind of a neat visualization. You can kind of see what the algorithm is doing. And I didn't draw the lines here because there are no lines, right? Every tag has some relationship to every other tag, and I didn't have to sort of put an arbitrary cutoff and say, well, if you have fewer than this many questions in common, I'm going to consider that you have no relationship, and if you have greater than this number in common, I'm going to consider that you have a very strong relationship. So this is the output of running a dimensionality reduction on Stack Overflow. This is the same data set as the Reddit map run through t-SNE. So here, each circle is a little sub-discussion board, a little topical Reddit discussion board, and the data set was essentially co-posting. So the input was basically which users posted to both, which users posted to which subreddits. And you can see that there's kind of, again, neat little clusters form. And one thing which is more apparent here than in the Stack Overflow visualization is that the smaller points, which are the less commented upon subreddits, are near the middle, which is kind of the opposite from what you get in a typical force-directed layout. In a force-directed layout, the center of the network, the most commonly linked to things tend to be in the middle in a big clump. Well, when you use dimensionality reduction in this kind of data set, it turns out that it actually projects most of the things to the edges. The short answer for those who are capable of visualizing in their heads a 100-dimensional space, which is not me, is that essentially the natural topology of this data set is kind of like one of those little slinky balls, one of those things that has like a little bunch of rubber hairs. So there's people who talk a lot about sports who don't talk about anything else. There's people who talk about music who don't talk about anything else. So there's lots of little dimensions that kind of pull out. And when you take a little, squishy slinky ball thing and squish it down to 2 dimensions, you get this kind of hairball. But the tip of each little hair is kind of a locus of interest. So you see the green blob in the right there. You've got NFL and hockey, and each of the little lines here essentially is a different sport. So if you were to zoom in, you see NBA, Major League Baseball. And near it, you see soccer. And soccer is a different color than the other sports. In fact, it's the same color as world news. Well, this is interesting because Reddit, like many places on the internet, there's a lot more American traffic than say, traffic in English from other languages. So it turns out that soccer actually has a lot more affinity with the UK and Ireland and Scotland than it does with the US, more US-centric leagues. And so soccer tends to be closer to that part of the world. You see that the orange cluster there on the right has music and drugs very close to each other. So instead of kind of clumping everything together in the middle, which is what force-directed layouts tend to do, dimensionality reduction tends to throw everything to the sides, but yet still retain a certain measure of sort of relatedness and connectedness. Another example I really like is there's a cluster around cars, right next to motorcycles, right next to bicycling, right next to male fashion advice, right next to guns. So there's some interesting patterns that you see there. So this is the output of t-SNE on, again, sort of a social network categorization kind of thing. But you can run dimensionality reduction algorithms on all sorts of data sets. This is maybe a little less fine-tuned output of what we did was we took all of the English language press releases from the last federal election, and we declared that each word in each press release was its own dimension, and we ran a dimensionality reduction algorithm, and then plotted the output. So each dot here is a press release by one of the major political parties that releases press releases in English, so not the block, and they're color-coded by the party. And so we went and kind of moused over and figured out what each of the little clusters were. And so you see this little cluster close to me here that says Justin is a whole bunch of press releases that all basically took the format, Justin buys a plane, Justin goes to Saskatchewan, Justin does this. None of the other parties had sort of peppy Justin buys a plane kind of press releases. You'll see that the Conservative talks a lot about the economy and the military. The Greens talk a lot about oil and the fact that Elizabeth May was not invited to the debates. So you can apply this to sort of textual data. You can apply this algorithm to image data. It might be a little hard to see. What we did here is we gave it a whole bunch of images of structures and kind of asked the algorithm to kind of lay out these images however it saw fit. And so you'll see you've got a bunch of igloos down in the corner. Next to igloos you have monuments, I guess because there's a lot of blue in them. Above the monuments you have sandcastles. This is my favorite part. Above the sandcastles you have actual castles. Picked up the difference between the relationship between sandcastles and actual castles. You've got, near the igloos, you've got huts, and then houses, and then high-rise buildings. So you can apply this kind of thing to very rich data sets without actually having to say there's an arbitrary sort of similarity between two images that causes them to be brought close to each other. So that's basically the end of my examples. I'm not saying that dimensionality reduction is sort of the be-all, end-all algorithm. It's just for certain types of data. If you find yourself taking your data set and sort of shoehorning it and throwing away some data and thresholding it in order to feed it into a graph layout algorithm, maybe the next time you're thinking of doing that, you'll remember this talk and kind of go check out some dimensionality reduction algorithms. So I'll be putting this online. I'll be putting the link to the video and the slides in the VisMtl meetup group, but I've got a couple lists of algorithms and tools and libraries for both graph visualization tools and dimensionality reduction. So when I say that it's really easy to do graph visualization, I really mean it. Gephi, GraphViz, super useful frameworks. If you want to do web, there's Sigma.js and D3.js. Make it really easy to publish graphs on the web. For dimensionality reduction, tends to be a little bit of more of a scientific kind of machine learning nerd domain. So there's a lot of algorithms with three-letter acronyms: principal component analysis, PCA, singular value decomposition, SVD. This works really well at parties. What do you do? Singular value decomposition. Yeah. And in terms of tools and libraries, MLDB, the machine learning database, is the product that I work on. It's built here in Montreal, and I'd love to help you guys use it if you're interested. But there's also scikit-learn, which is a Python library, and the R project, which is another sort of data analysis environment. MLDB is also open source, so I'm not here just plugging my corporate thing here. That's basically the end of my talk. Thank you very much.
For 5 minutes maximum.
Sure.
Thanks for the talk. I'm new to t-SNE, I've never used it before, but I work with dimensionality reduction and I've used a lot of principal components analysis. And one nice property of PCA is that it's easy to interpret the axes of the two-dimensional graph you get, linear combinations of features. So in t-SNE, is there any easy way to understand what X and Y mean?
No. PCA is essentially, much like SVD, is kind of a rotation and stretching kind of dimensionality reduction. t-SNE is nice to run on the output of PCA because it kind of allows you to look at all of the things together. So if you do PCA or SVD down to 100 dimensions from 50,000, you still have a 100-dimensional space to go look at. So the standard way I do this is essentially I run SVD first to get a dense 100-dimensional matrix, and then run t-SNE to get a 2-dimensional one. But it's kind of a complement. It's sort of a high-level overview.
I'm not sure if you mentioned it, but I want to give this graphs. Did the color encode information?
So the question is, did the color encode information in any of my images? Yes. I kind of skipped over it just for brevity, but in all the images that were generated by me, what I did was I ran a clustering algorithm. I ran k-means in a sort of the high-dimensional space to get proximity, and I colored them by cluster. The next question I usually get is, how many clusters were there and why? The answer is there were 20, and that's because I have a nice 20-color color scale, and I don't think people can really perceive the differences between more than about 20. So there's not sort of any endemic reason why I use 20. It's just the color scale that I've got.
I was wondering, maybe it's a stupid question, but are these algorithms deterministic?
The question is, are the algorithms deterministic? Many implementations of these algorithms are non-deterministic. They depend on a random seed, but you can run them with the same random seed. Yeah, and there are some interesting sort of meta multi-dimensional analysis algorithms that sort of try and capture the differences between different runs to capture different sort of facets. But in general, most implementations will not be deterministic.
Yeah, that's the main point. Like, depending on the run, you will get very different results, and then you're basing your interpretation on one instance of like infinity of instances.
Yeah. So for analysis, it's challenging to do good analysis based on the output. I would say this is good for kind of a first level overview of a high dimensional data set to kind of get a sense. Usually, if there's some kind of clustering or some kind of structure to the t-SNE output, there's probably some kind of structure to the underlying data. It's kind of more of a hint. It's a bit directional. I wouldn't really base any strong analysis based on the output of t-SNE. I would base strong analysis based on the output of PCA or SVD.
Someone who just kind of scratched the surface of this kind of stuff, the first introduction to clustering they usually get is k-means clustering, right? You didn't mention that. Is that because it's just not a good thing? It's just kind of something for beginners, or what would be the value of k-means versus all those other things?
So the way I did the colors in these graphics was actually with k-means clustering.
Okay.
The answer is probably a bit longer than I can give right here, but I can talk to you after. But I mean, basically, there are a bunch of different clustering algorithms, some of which work best in spaces which have been normalized, or where you expect there to be equal-sized clusters, or clusters of a certain shape. So the short answer to your question is nothing wrong with k-means clustering. We use it all the time, but there are certain situations where it won't work very well. One more. Sure.
Does t-SNE have any tuning parameters, or is it just a...
Yes, and they have awesome names like perplexity and learning rate. So yes, there are some, and you can play with them. Basically, you'll get sort of more or less clustering, more or less kind of clumping. Clustering is the wrong word, but it's got a bunch of interesting parameters that you can spend lots of time playing with. Thanks very much.
Merci beaucoup, Nicolas. Merci. While Chris is getting set up,